Good morning, everybody. We're going to get started. Welcome back. It's great to see everyone, and we have a lot of fun things to talk about today. We have a set of 3 speakers, and our first speaker today is Brooke Wolford. She earned her PhD in bioinformatics from the University of Michigan in 2021, where she was on the Genome Science Training Grant and also had Mike as her PhD co-advisor. She's now the Skłodowska-Curie Postdoctoral Fellow at the Norwegian University of Science and Technology, Hunt Center for Molecular and Clinical Epidemiology. Her research focuses on statistical genetics, precision medicine, and large-scale biobank analyses, particularly multi-ancestry analyses of cardiometabolic traits. Welcome, Brooke.
Thank you. Hi, everyone. It's really nice to be here, and thank you so much for the honor of being invited. Today, I'm going to talk to you about my work to advance precision public health with genomics, proteomics, and electronic health records. But first, I wanted to highlight how important Mike has been to my career trajectory. So this is actually the first paper that we were on together, and I was a postbac at the NIH in the Collins lab working with the fusion study. So this is from 2014, I believe. And when I was trying to decide where to go for graduate school, I was really torn, but ultimately there was no better place for statistical genetics than the University of Michigan. And as we've established, that's a lot thanks to Mike and his cultivation of a research environment and a training program that was really excellent. So I was, as was just said, I was co-supervised by Kristen Weller and Mike Boehnke. And then the next part of my career trajectory is also thanks to Mike. So as I understand it, I'm finishing up a postdoc at NTNU, and I work with the Hunt study. And as I understand it, about 20 years ago, Mike and others were interested in getting some genotype data from the Hunt study for a GWAS of type 2 diabetes. And so they connected with my current supervisor, Christian Vim. And at some point, one of his PhD students came over to Michigan and learned from the best. And then that collaboration evolved, and Kristen Weller ultimately worked on genotyping and imputing a lot of Hunt. And so I think that me choosing to go work with the Hunt study would never have happened. That collaboration would never existed without Mike. So I can really trace his influence on every step of my training, and I'm excited to talk to you about the work I've been doing. So the Hunt study, for those of you who may not be aware, is the Trøndelag Health Study. And this is a biobank in central Norway, and we have participants that go to 3 different hospitals, so we're able to link to the electronic health record of those individuals. There's also a very high participation rate for this biobank. People are really excited to be a part of biomedical research. It's also a genetically homogeneous population, which can be good for statistical genetics, and low immigration rates as well. We can also link to national registers, as can most Nordic countries, and we have longitudinal questionnaire and measurement data. And this figure is just showing how that works. So since the 1980s, there's been 4 enrollments roughly every decade, and different subsets of individuals have omics data and other measurements. We have DNA data on about 90,000 individuals, and there's several participants that have been in all 4 Hunt enrollment periods, and we're gearing up for Hunt 5 soon. So a lot of the results I'm going to talk to you about today are from the Hunt study, also from FinGen and the Michigan Genomics Initiative. So I'd like to take a step back and tell you a little bit about some of the trends that motivate my research in precision public health. So this is a plot showing for total CVD and stroke. The prevalence on the left side here relates to the bars, and then the numbers of individuals affected relates to the points. And for each pair, it's now and in 30 years. So we have this projected increase in prevalence over the next 30 years for total CVD and stroke across all age groups. And within total cardiovascular disease, I'm going to be talking today about coronary heart disease and heart failure, as well as diabetes. So for all of these, there's this projected increase over the next 30 years. But interestingly, the global burden of disease estimates that 76 to 79% of the total disability-adjusted life years are attributable to modifiable risk factors. So there's still work that we can do to prevent some of this increase in prevalence. To do that, I think we should be a bit better at prediction. So to give you the state of the art for cardiovascular disease prediction in Europe, we use something called SCORE2. And this is a 10-year CVD risk metric that is used for people without prior cardiovascular disease or diabetes, and only from age 40 to 69 years. There's a SCORE2 older persons, that is for individuals 70 and over. These are just the risk tables with high, medium, and low risk based on sex, smoking status, blood pressure, and non-HDL cholesterol. The diabetes equivalent of this is the Finnish diabetes risk score. So this is a prediction of diabetes that can be done without any measurements, and it's used to identify individuals at high risk. Interestingly, Norway has recently moved away from this score. They now just advocate for an HbA1c measurement if they think someone is at high risk. They didn't think that this metric was sensitive or specific enough. And I think the main limitation there is you have to be interacting with your doctor to be identified as high risk. There's no age-based or universal screening. So that's where things stand for current conventional risk factors. But we've been saying for over a decade that we'd really like to have some precision public health, providing the right intervention to the right population at the right time. And so my research aims to advance that goal. So, we have these risk factors and we'd like to intervene so we can reduce individuals' risk. And I'd like to improve upon these conventional risk models I've mentioned. I've mostly been working with polygenic scores and also proteomic risk scores, and then more recently with clinical risk scores from electronic health records. So today I'm going to give you 3 stories, one about each of these data types. So polygenic scores are coming from genome-wide association studies and genetic data, proteomic risk scores from the blood plasma proteome, and clinical risk scores from diagnosis codes from the electronic health record. So we'll start with polygenic scores. At the beginning of my postdoc, I worked with the Intervene Consortium, and we were interested in seeing how risk estimates of a polygenic score varied by age and sex, and what the implications were for the cumulative incidence estimates. So this was a big group effort. These are the main analysts from the partner biobanks that I'm showing here. And I wanted to highlight what a polygenic score is for those of you who may not work with this type of data. So essentially, it's a weighted sum of individuals' risk. So here I'm showing a locus zoom plot for the CDK and 2B, and we have this effect estimate from GWAS. We can then take a weighted sum of this effect estimate and an individual's risk alleles and look over the whole genome. So we can add in PCSK9, we can add in ApoB, and ultimately, after adding up millions of markers usually, we have this weighted sum of a polygenic score, which looks like a normal distribution. And we can make some cut point, top 5th percentile, top 10th percentile, and individuals that fall in that group often have a very high risk of disease, and as Dr. Shork mentioned yesterday, it can often reach that of a monogenic mutation. So we set out to harmonize phenotypes for 18 different diseases that we thought had a high global burden, and then we calculated genome-wide polygenic risk scores using a method called MEGA-PRS. These weren't necessarily the most optimized polygenic risk scores for each trait. We just wanted to have a consistent score to look at across all the phenotypes. Then each analyst that had access to the individual level data estimated hazard ratios with Cox proportional hazards models for those scores. And they did that on a full sample basis and also on age and sex specific groupings. Now, you might know that a lot of times biobanks have healthy bias. They're not necessarily representative of the population. So we wanted to recalibrate our estimates to hopefully be more indicative of the risk of that country. So we took country-specific estimates for mortality, prevalence, and incidence from the global burden of disease. And so we were able to use those to recalibrate our cumulative incidence curves to make country, sex, and age-specific cumulative incidence estimates. So here I'm showing the meta-analyzed hazard ratio per standard deviation of the polygenic score on the x-axis, and I'm highlighting here coronary heart disease and type 2 diabetes. So we actually saw pretty widespread sex-specific effects. Those are all indicated by the stars. And we also saw age-specific effects. So here I'm showing Individuals in the youngest quartile are in yellow, and individuals in the oldest quartile are in purple. And we see this attenuation over age. So individuals that are younger, there's a higher effect size of the polygenic score. And this has been seen in other work as well, but it's pretty consistent across all the traits. Colorectal cancer is a bit an outlier here, but you see it really nicely for coronary heart disease. So we can take those hazard ratios and estimate cumulative incidence. So here I'm showing cumulative incidence curves for type 2 diabetes. And we did this in the FinGen study because it was the largest cohort within Intervene. And the blue line is the top 1 percentile of the polygenic score. The red line is the bottom 1 percentile, and the black is the median. And this dotted red line here is the cumulative incidence of the average Finnish population at the start of the American Diabetes Association screening for T2D. So they think you should screen at 45 years. So we tried to calibrate that to Finland. And what you can see is that individuals in this top 1 percentile, they reach this red line at 22 years for females, and for males at 24.8. So we think that individuals in this top risk category really could benefit from earlier screening. Meanwhile, individuals in the bottom 1 percentile basically never reach that cumulative incidence by age 80. So if we want to do some risk-informed screening for diabetes, polygenic scores could be a useful tool. We dug into this a little bit more in the Hunt study. So we were able to look at different age bins here on the x-axis, and the y-axis is the hazard ratio per standard deviation of the polygenic score. And this time we were able to adjust for a lot of conventional risk factors that are associated, and this is for coronary artery disease, so I'm switching gears a bit to a different phenotype. So there's 2 things I want to point out. One is that in this case, males and females actually had pretty similar effect estimates across each of the decades. There's a bit maybe more marked difference at these bins here. And we also still see that attenuation over the age. So as both males and females age, the effect of the score decreases. But as I mentioned, score 2 and the score 2 older persons are for this part of the population. And luckily, it's this lower part, younger part of the population where the polygenic score has the most effect. So we're really thinking that this would be the good portion of the population to look at with the polygenic score as some means of screening tool. If we, again, take those hazard ratios to cumulative incidence, here I'm doing tertiles. So this is the top tertile cumulative incidence for coronary artery disease, and the middle and the bottom. The polygenic score is a nice complement to existing conventional risk factors. So if we add in family history, each of those curves is essentially bifurcated into individuals with positive family history and negative family history. And we also see the same for score 2, and for LDL, and for age. So definitely not thinking that polygenic score should replace the existing conventional risk factors. They're both complementary measures that give us more specific estimates of the cumulative incidence for these groups of people. So polygenic score is nice because you can measure it once at the beginning of life and use it again and again. But proteomic risk scores, or the plasma proteome, can be a little bit more temporally relevant. Maybe you can pick up disease closer to the onset. And it's also a bit closer to disease etiology than genetics. So myself and others in the field have been looking into proteomic risk scores, especially as there's finally enough proteomics data to do this. So we set out to predict incident type 2 diabetes with the plasma proteome in the Hunt study. And to do this, we actually repurposed some existing proteomics data that was for a cardiovascular disease study. And we were able to take we had SomaLogic, 5,000 proteins measured, and this was from the Hunt3 survey. So we were able to look backwards and forwards with the electronic health record and remove prevalent type 2 diabetes cases based on an ICD code diagnosis, and then look at these incident type 2 diabetes cases within our data. So here I'm showing this volcano plot with the significant proteins here colored by individual or proteins that were associated with reduced abundance with type 2 diabetes or increased abundance with type 2 diabetes. And the x-axis here is the odds ratio per 1 standard deviation increase. So we see a lot of the normal suspects, which was a good sign. So the IGF binding protein, SILP2, and plexin B2, if you look at other proteomic association studies, those are often up at the top. And we were able to adjust for a lot of potential confounders and covariates, including CVD, which was the original study selection criteria. So after doing Benjamini-Hochberg adjustments, we had 308 proteins that were significant. And we took 3 published studies of incident type 2 diabetes that were on the same proteomic platform. And we had 239 aptamers that were significant and in the same direction in at least one of those studies. So this was just to get a sense of, can we reuse this data? Are we finding things that make sense? And we profile a little bit of some potentially novel findings. But we were really interested in prediction. So we took our data and we split it into a testing and training set. And we again did this logistic regression, 1 regression per protein. And we only considered aptamers that had this, were still significant after adjustment for multiple testing. Then we did feature selection with lasso regression and a 5-fold cross-validation to optimize our shrinkage parameter. And we took those coefficients forward in the test set to predict type 2 diabetes status, and we assessed discrimination using the area under the receiver-operator characteristic curve. So here I'm showing those AUC results for several models that we looked at. So these top 3 are ones that used the proteins. So proteins only, proteins plus our covariates, and then proteins plus the covariates plus the polygenic score for type 2 diabetes. And you can see that those are all different, significantly increased AUC over the covariates only and the covariates plus the polygenic score. So looks like the plasma proteome helped us discriminate type 2 diabetes cases, and we can just visually see those curves here. There's a bit of an overlap in the 95% confidence intervals, but you can see these 3 curves are clustering quite nicely, the ones that have proteins. I was a bit surprised that we didn't get this bump with polygenic scores plus proteins, because some other studies have shown that, particularly for cardiovascular disease. But because we did lasso regression, I have the feeling that a lot of the proteins that were correlated with the polygenic score are kind of dropping out. And so we're looking into this further to see if we can get an increase when we look at proteins plus genetics using some different models. I wanted to sort of dig into what was the important feature that was selected for each of these models. So here I'm showing on the x-axis the importance, and these are proteins, and I know they're quite small. The idea here is that you can see there's sort of 10, 20 proteins that really have a larger coefficient here. But when you add in the covariates, they're completely outweighed by waist-height ratio. And then sex as well. But the SILP2 protein is still hanging in there. And then when you add in genetics, it's also way more important than a lot of our other features. So of course, because of the way lasso works, this isn't a perfect analysis, but if we just think about the important features that seem to be consistently up at the top, it looks like these 3 covariates, clinical risk factors, are important, and these 5 proteins seem to be quite consistently important for the feature selection. So the idea here is that we probably can't afford to do a proteomics profile that profiles thousands of proteins. We'd like to find a sparse proteomic risk score. And so maybe we could dig into if these 5 proteins would work. So as we continue to work more on the proteomic risk score, I've also gotten interested in clinical risk scores using electronic health records. And this was actually because I was brought in on a project based at Michigan. So we set out to ask how clinical and genomic risk predictors compared for heart failure prediction. And this was a study led by Zhu Shi at the Biostatistics Department and Kristen Willer, and one of my colleagues from the Willer lab as he was finishing up his PhD. And he's now at Regeneron. So we used several cohorts within the Michigan medicine system. The first was the primary care provider cohort, and this was used to have this access to a rich medical history of recent visits since 2018. We had a heart failure cohort that had this phenotyping algorithm run on it, so we had sort of a gold standard heart failure outcome. And some subset of that overlapped with the Michigan Genomics Initiative. So for those individuals, we had both a good phenotype and genetics information. So without going too deep into the details, the idea here was to take natural language processing and look at the co-occurrence of diagnosis codes in the electronic health record. So here in this example, if we had ischemic stroke and hypertension, we could look at how often those two ICD codes occurred near each other. And this is just this idea of finding a main word and a companion word co-occurring. So we were able to do that by taking this structured data, the diagnosis codes from the electronic health record, and creating these code embeddings with this natural language processing. We then performed lasso regression, again, for feature selection. So we were able to shrink 500 to 350 of the most relevant latent phenotypes that were representing heart failure. And then we were able to take the coefficients from this and create one clinical risk score per individual. So the way this worked was we took these primary care provider set as our derivation set. That's where the natural language processing was run for the medical code embeddings. And then using that phenotype definition from the phenotyping algorithm, we were able to define the clinical risk score weights. And then we took those forward into this test set for validation. And then we could integrate a polygenic risk score for heart failure, which came from the Global Biobank Meta-Analysis Initiative, and the clinical risk score. And we did this with a tenfold cross-validation area under the curve. We were interested in how many years before diagnosis we could find like a signature of heart failure in the electronic health record. So for cases, we would vary X from 1 to 10, going back in time before diagnosis. And for controls, we anchored on the last ICD code in the electronic health record. And again, then had this subset of the data that we could use for the clinical risk score. So sorry this resolution is poor, but on the x-axis here is going to be the year prior to heart failure diagnosis, and on the y-axis is the tenfold cross-validated AUC. So the black point here is baseline if we just use age and sex to predict heart failure. The orange line is the polygenic risk score, so that's already getting us a little bit better discrimination. And the gray line is this ERIC heart failure risk score, which is the conventional risk score for heart failure. And then in blue is our clinical risk score. So 1 year before diagnosis, the clinical risk score from the electronic health record is outperforming the conventional score. And we get a slight bump in the AUC when we add polygenic risk score to that clinical risk score. So we see this similar trend for the first few years, but then the clinical risk score becomes a lot less informative as we move back in time before diagnosis, as we might expect. So we can say that at 3 years, the clinical risk score is having better discrimination for heart failure compared to the ERIC score. So we were interested in running this in the Hunt study, and we did, but the area under the curve was really disappointing. And I think part of that has to do with the diagnosis codes used between the US and Norway. They're slightly different, and we had weights per code, so we had to do some matching the best we could. And yeah, maybe some other situations with how our healthcare system is. So around the same time, foundation models have been being published using other electronic health record data. And a lot of that was more harmonized on a type of code or vocabulary that maybe would be a better match. So I've actually been working with a bachelor student who has processed our electronic health record data into SNOMED codes. And so for those of you who may be aware, there's this observational medical outcomes partnership that has this common data model. And I think it will be the future for trying to harmonize across hospital systems so that we can have these models that can work in different contexts. So we used the standardized vocabulary, SNOMED codes, and we converted our ICD codes to that, and then we can match that up with other published models. So we downloaded a model called MOTOR, which was trained on the Stanford healthcare system, and this was actually a time to event foundation model. And we were able to extract embeddings for all of our participants. There's about 700 embeddings that the model estimates. And then we took those embeddings forward just to a simple random forest to do a binary classification on heart failure. So here again, I'm showing this area under the receiver operator characteristic curve, and on the x-axis is the time before diagnosis. So using just the embeddings in purple, we have slightly higher discrimination than just using age and sex alone, although age and sex was performing quite well for heart failure. And you can also see this attenuation as the time horizon increases. So we're working on this. This is brand new data, and we're looking at polygenic risk score in addition to this. And there's several other models that are out there now that we'd like to benchmark as well. So I've highlighted these 3 different modalities for risk predictors, but how do we actually use them, and like what comes next? So I think there's a lot of future steps. I've highlighted here just discrimination metrics, but it's really important to also look at calibration and also clinical utility. For polygenic risk scores, we're starting to talk more about sex-specific effects, but for proteins, for example, I was looking at everyone together. So I think sex specificity is going to be important, and also temporal relevance. So when in the life course are these different predictors useful? How early before diagnosis are they useful? And then transportability, as I mentioned, different healthcare systems have these unique problems based on how the data might be encoded, but also all of the work I've shown today is from individuals that have genetic ancestry similar to European reference populations, and so we would also like for all of these to work well across global populations and contexts. I think it's also really important to think about integrating all these together. To some extent, we've been adding polygenic risk scores to clinical risk scores or polygenic risk scores to proteomics, but how could we, if we had a sample of individuals, use all of them together? Cost effectiveness is also very important, especially in Norway and places with a public healthcare system. So are these actually useful at preventing disease? And how do we actually integrate them into the clinical healthcare system? So the clinical risk score is kind of nice. It could just operate in the background of the electronic health record, and you don't really have to be doing much. You just update people's risk over time. But of course, things that take measurements have more of a barrier to integration. So I'm highlighting here my funding and collaborators on the main projects that I've talked about, and I especially like to thank my trainees that helped with this work and highlight the research team at the Hunt Center for Clinical and Molecular Epidemiology. And I would like to thank Mike for everything he's done to make this research possible, to be honest, and thank you all for your attention. Thank you.
I was pleased you highlighted heart failure, which is a growing and serious matter. But there's a big dichotomization on normal ejection fraction versus the expected decreased ejection fraction.
Yeah.
With the normal ejection fraction being the more troubling problem.
Yeah.
Have you looked at that dichotomy?
No, we haven't, but we have a subset of our individuals that have had really detailed heart failure diagnoses so that we can tease that apart. This was just a kind of catch-all ICD code outcome, but that's our hope is that we have about 2,000 patients that we have that detailed information in a clinically adjudicated definition, and that's really important. The other thing I can highlight is that the polygenic risk score was also for all heart failure together because it's been harder to work across biobanks to harmonize that definition. So that's another place that needs improvement is a polygenic score that really is coming from the main subtypes of heart failure. Yeah, thank you for that question. Yeah.
Have you tried, I think it's called trial emulation, where you take all your data and then try to do clinical trials? Because if you look at, the public health system, can you go into your data and then say, okay, how would your heart or cardiovascular risk change if you stopped smoking now? Or how would this change if you lost 50 pounds or 20 pounds or whatever? So I think in the end, people don't want to know when is my risk of dying of heart failure. People want to know what can I do. Can you do it that way and therefore convince also health system, why it may be very useful to play around with these data.
Yeah, that's a great question. I haven't looked at that, but some folks in my center have done some target trial emulation work. And yeah, I think that's highlighting a huge gap is if this just is general risk, then what do you do? Is it weight loss? Is it medication? Is it smoking cessation? And I hope that some of these risk predictors can also be kind of partitioned into that exact risk so that you actually have the precision intervention and not just the person.